given that this process is at constant temperature, that means that Q equals delta H for this particular system. And so we just calculated that delta H here equals, well, we know it equals Q, and it equals 12,040 joules. Okay, that's what this is right here. This is the reversible heat because it's done reversibly, but that's okay. Everything we've looked at so far has been reversible heat flow. Don't worry about that. What then is the change in entropy for the system? Well, we have defined the change in entropy to be equal to the reversible heat flow divided by the temperature. Okay, so since we have this definition, this quantitative way of expressing change in entropy, then if we know that this is necessarily the reversible heat flow, we've just calculated that, then for this particular system, then we know that the change in S for this particular system is going to equal that amount of heat, 12,040 joules, divided by the temperature of the system. What was the temperature of the system? The ice melting, it stayed constant at 0 degrees Celsius. Now, if I put a 0 here, then this is going to be undefined. So always when we're looking at this particular formula, the heat divided by the T, the temperature has to be absolute. Absolute. Always. Okay? So that means that we have to express it in an absolute scale, which is the Kelvin scale. All right? Always, always. So rather than say over 0, which is not defined, we use the absolute scale because that's how the entropy is defined. Then that is 273 Kelvin. All right, so now we have that. So I can calculate the change in entropy by calculating this particular value. It's going to equal about 44 joules per Kelvin. So I've just calculated the change in entropy for the system. Now, what is the heat from the perspective of the surroundings? What is the heat flow? That means did the energy of the surroundings go up, down, or by how much? In this case, since my surroundings was in thermal contact with my system, and I know that my system absorbed 12,040 joules of heat energy, then I know that that must have come from my surroundings. So my surroundings gave off that same amount. So when I express that heat given off by the surroundings, it's going to be the same as that was absorbed by the system, but the sign is going to be opposite because the surroundings gave off heat. And whenever any system gives off heat, whether that be the surroundings or the system, any defined state, that's going to be a negative value. So the amount of heat energy that was given off by the surroundings is the amount of heat energy that was absorbed by the system. So that's a negative 12,040 joules. So given that I know the heat given off by the surroundings, what is the entropy change for the surroundings? Well, the change in entropy simply equals the reversible heat, and this is reversible, divided by the temperature. So that's going to be a negative 12,040 joules. Now, what was the temperature of the surroundings? Do you remember? That was room temperature. That's 298 Kelvin. So I can very easily calculate the change in entropy of the surroundings. It's about a negative 40 joules per Kelvin. Okay, so now I've got the entropy, change in entropy of the system and the surroundings. So what is the entropy change for the universe for this particular process? The change in entropy for the universe is equal to the change in entropy for the system plus the change in entropy for the surroundings. Okay, and so remember the second law says if the change in entropy of the universe is a positive change, if the energy of the entropy of the universe is increasing, then it's going to be a spontaneous change. And that's the definition, that's the second law. So I can put in my value for the system. It was 44 kilojoules excuse me, not kilojoules, it was 44 joules per degree Kelvin. That was the system. The surroundings is negative 40 joules per Kelvin. And that is going to equal the change in entropy of the universe is going to equal a positive 4 joules per Kelvin. All right. So the answer to part 8 is extensive. That is, it was for 36 grams. It was positive, so indeed this change is spontaneous. But what is the entropy change per mole of solid ice that melts under these conditions? Well, this particular spontaneous change that we just calculated was per 36 grams, because that's what the heat was. So as it turns out, let me see, if we want to calculate per mole, then we would just go back to the situation that for each mole, the system, the change in enthalpy is just 6.02 kilojoules per mole, divided by 273, that's the temperature is 0 Kelvin, that equals 22 joules per mole per Kelvin. The change in entropy for the surroundings, in this case, for the surroundings, is the same amount of energy, 0.602 kilojoules per mole, divided by 298, which equals 20 negative, and it's negative. That's a negative 20 joules per mole Kelvin. So in this case, the change in energy for the change in entropy for the universe is going to be 22 minus 20, which equals 2 joules per mole Kelvin. That would be the change per mole of the universe for melting ice. Okay, and then the last question here is, it says the total entropy change depends on the process. Would you expect a larger or smaller total entropy change if the surrounding had a constant temperature of 0.1 degrees Celsius? In the case that we just looked at, the system was at 0 degrees and the surroundings were at, which is, I should say, 273 Kelvin, and the surroundings were at 298 Kelvin. This question is wondering if the system was at 273 and the surroundings were, at this case, 273.1 Kelvin. Would I expect a larger or smaller entropy change for melting under these conditions versus melting under the original conditions? Well, since the temperature change is less, actually a smaller change in entropy. Nevertheless, it's still going from a warmer to a cooler. It's going to be a positive change, but it's a smaller change in entropy because the calculated values now are closer. So it's a smaller change in entropy. So the amount of the change in entropy depends on the conditions under which the change occurs.